Good morning, everyone. Welcome back to Chemistry 101. Today, we're diving into Chapter 3, Chemical Reactions. This chapter will provide an in-depth exploration of chemical reactions, including how to balance equations, the types and characteristics of different reactions, and the principles underlying dissociation, precipitation, acid-base, and redox reactions. Understanding these concepts is crucial for mastering high school, honors, and AP chemistry. Let's get started. Balanced chemical reaction equations. Introduction to chemical equations. Chemical equations represent the transformation of reactants into products in a chemical reaction. They provide a concise way to describe chemical processes and must reflect the conservation of mass, meaning the number of atoms for each element must be the same on both sides of the equation. Steps to balance a chemical equation. Write the unbalanced equation, identify the reactants and products and write their chemical formulas. Example: hydrogen reacts with oxygen to form water. H2 plus O2 goes to H2O. Count atoms for each element, count the number of each type of atom in both reactants and products. Add coefficients to balance atoms, adjust the coefficients, numbers in front of chemical formulas, to ensure that each element has the same number of atoms on both sides of the equation. Balanced equation. 2H2 plus O2 goes to 2H2O. Verify the balance, check that all elements are balanced and that the coefficients are in the simplest whole number ratio. Importance of balancing equations. Balancing equations is essential for accurately calculating the quantities of reactants and products involved in a reaction, understanding reaction stoichiometry, and ensuring compliance with the law of conservation of mass. Dissociation and precipitation reactions. Dissociation reactions. Dissociation reactions occur when ionic compounds dissolve in water, breaking apart into their constituent ions. These reactions are fundamental for understanding how substances behave in aqueous solutions and are key to many biological and chemical processes. Example: dissociation of sodium chloride in water. NaCl, S, goes to Na, Aq, plus 1 plus Cl, Aq, minus 1. Significance: dissociation allows ions to participate in further chemical reactions, such as forming precipitates or conducting electricity in solutions. Precipitation reactions. Precipitation reactions occur when two aqueous solutions react to form an insoluble solid, known as a precipitate. These reactions are driven by the solubility rules, which predict the formation of precipitates based on the solubility of ionic compounds. Example: reaction of lead, 2, nitrate and potassium iodide to form lead, 2, iodide precipitate. PbNO3, 2, Aq, plus 2Ki, Aq, goes to PbI2, S, plus 2KNO3, Aq. Applications. Precipitation reactions are used in water treatment to remove contaminants, in qualitative analysis to identify ions in solution, and in the synthesis of various chemical compounds. Introduction to acid-base reactions. Acid-base theories. Acid-base reactions are fundamental chemical processes that involve the transfer of protons, H ions, between reactants. Different theories explain these reactions. Arrhenius theory: acids produce H ions in water, while bases produce OH1 ions. Bronsted-Lowry theory: acids are proton donors, and bases are proton acceptors. Lewis theory: acids accept electron pairs, and bases donate electron pairs. Neutralization reactions. Neutralization reactions occur when an acid reacts with a base to produce water and a salt. These reactions are critical in various industrial and biological processes. Example: reaction of hydrochloric acid with sodium hydroxide. HCl, Aq, plus NaOH, Aq, goes to H2O, L, plus NaCl, Aq. Applications. Neutralization reactions are used in antacid medications to neutralize stomach acid, in agriculture to adjust soil pH, and in industry to treat acidic waste. Electron transfer reactions, redox reactions. Definition of redox reactions. Redox reactions, or oxidation-reduction reactions, involve the transfer of electrons between substances, resulting in changes in their oxidation states. These reactions are crucial for understanding chemical reactivity, energy production, and biological processes. Oxidation and reduction. Oxidation, the loss of electrons, leading to an increase in oxidation state. Reduction, the gain of electrons, leading to a decrease in oxidation state. Identifying redox reactions. To identify a redox reaction, follow these steps. Assign oxidation states, determine the oxidation states of all elements in the reaction. Identify changes in oxidation states, look for changes in oxidation states to determine which substances are oxidized and reduced. Example of a redox reaction. Example, reaction of zinc metal with copper, 2-sulfate. Review the equation then observe. Oxidation, Zn is oxidized from 0 to +2. Reduction, Cu superscript 2 is reduced from +2 to 0. Applications of redox reactions. Energy production. Redox reactions are the basis of electrochemical cells, such as batteries and fuel cells, which convert chemical energy into electrical energy. Metabolism. Biological redox reactions are essential for cellular respiration and photosynthesis, processes that provide energy for living organisms. Real-world considerations and modern-day applications. Balanced chemical equations. Balanced chemical equations are crucial for predicting the outcomes of reactions, calculating reactant and product quantities, and ensuring safety in chemical processes. They are foundational for stoichiometry, which is used in laboratories and industry to optimize reactions and minimize waste. Dissociation and precipitation reactions. Water treatment. Precipitation reactions remove contaminants from water by forming insoluble compounds, aiding in purification and environmental protection. Pharmaceuticals. Dissociation reactions facilitate the delivery of active ingredients in medications by enabling ion formation in bodily fluids, enhancing absorption and efficacy. Acid-base reactions. Agriculture. Neutralization reactions adjust soil pH to optimize plant growth, improving crop yields and food security. Medicine. Acid-base reactions are essential in maintaining pH balance in the human body, affecting enzyme activity in metabolic processes, with applications in diagnostics and treatment. Redox reactions. Energy production. Redox reactions drive batteries and fuel cells, providing power for electronic devices and vehicles, and supporting the transition to renewable energy sources. Environmental science. Redox processes are used in bioremediation to clean up contaminated sites by breaking down pollutants into less harmful substances. Conclusion. Today, we explored the fundamental concepts of chemical reactions, including balanced equations, dissociation and precipitation reactions, acid-base interactions, and redox processes. These concepts are foundational for understanding chemical behavior and have numerous practical applications in science and everyday life. Mastery of these topics prepares you for more advanced studies in chemistry and related fields. Thank you for joining today's lesson on Chapter 3, Chemical Reactions. Stay tuned for our next chapter. Don't forget to like, subscribe, and share this video. Until next time. Dr. Siegfried Howell.